Okay, welcome to the lecture An Introduction to Large Deviations, and today we discuss the exponential equivalence. It is section number 11 in the lecture notes on my webpage. Is exponential equivalence. And the idea of the lecture today is that sometimes it is convenient considering one family of random variables, replace it by another family of random variables for which the large deviation principle is easily to obtain, and then get a large deviation principle for another random variable. And if these two families are sufficiently close, that one can show that the large deviation principle is not changed. It is the same. So therefore, today we want to discuss this kind of sufficiently closeness that doesn't change the large deviation principle when you go from one family to another family. And I want to start this lecture with the following example. It is example 11.1, and here we consider a stochastic differential equation. The large deviation principle for some kind of stochastic differential equations we already obtained 2 lectures ago, and today I would like to consider a little bit another equation. I would like to somehow spoil it. Assume that we have two functions from R to R that are bounded Lipschitz continuous functions. Are bounded Lipschitz continuous. We further assume that W is a Brownian motion. T, for T from 0 to capital T, is a Brownian motion. And then we consider the following stochastic differential equation. Dx epsilon, that depends on the parameter epsilon. It is A of x epsilon t dt, and then plus square root epsilon d Brownian motion. And the solution starts at 0, for instance. X epsilon of 0 is equal to 0. It is for every epsilon, for all epsilon that is larger than 0. And we showed with you that the solution of this equation, where you have the drift plus the noise, satisfies the large deviation principle, and we computed the rate function precisely. And now I want to a little bit like perturb that equation and put here epsilon and then the coefficient b of x epsilon t dt. And now you see that with this new term, we have a new situation, we have a new equation, and the question is, what is the large deviation principle? Does this equation satisfies large deviation principle? If it satisfies, what the rate function is, and so on. But first of all, let's try to understand how far away solution of these equations are to the solutions of the equations that we considered before. So let's compare. The solutions to this equation, x epsilon with with the solution to the equation d z epsilon t is equal to a z epsilon t dt plus square root epsilon Brownian motion, for which we proved the large deviation principle. And also the solution started from the same point, 0. And if it turns out that these two solutions are not far away, probably there is a chance also to get the large deviation principle. Therefore, we need to understand how far away they are. And let's do the comparison. And here we will use the same approach as we used when we worked with this equation 2 lectures ago. We want to use the Grunwald inequality. So we start with the comparison of, or from the estimate of the difference of two solutions. We put the absolute value and then consider x epsilon t minus z epsilon t. And using the fact that x and z are solutions to the stochastic differential equation, it means that they satisfies x satisfies z equality in the integral form, and z satisfies z equality in integral form, or in another words, that x epsilon, it is written, it is an integral here, integral z, and also here integral. And the same for z. Therefore, writing the absolute value of difference, you will have the absolute value of integrals. And I will write them. It is for the first, for x, you have x epsilon s ds, and I'm sorry, plus epsilon b x epsilon s, and then ds. Then you will have the Brownian motion square root epsilon wt, and then minus dt, and then minus integral from 0 to t a z epsilon of s ds minus square root epsilon wt. You see that the w will cancel each other, and then you can combine this term with that term, and more, and you can use also the triangle inequality. Therefore, we have the estimate, the following estimate. It is absolute value of integral from 0 to t a x epsilon of s minus a of z epsilon of s ds, and then plus epsilon integral from 0 to t b of x epsilon of s ds. But then you can move also the absolute value inside, and you can use the Lipschitz continuity. Therefore, we get L, the Lipschitz constant for A, and then integral from 0 to t. And here is x epsilon of s minus z epsilon of s ds, and plus, and then you will have epsilon and supremum norm of the function p for t from 0 to capital T. And you see that we estimated the function, non-negative function dependent on t, by the integral of this function plus some constant. And then using the Grunwald inequality, we get, by Grunwald inequality, we get that the absolute value of x epsilon of t minus z epsilon of t is less or equal than this constant which we obtained here. It is epsilon norm b c t, and then e to the power l. And that is for every t from 0 to t. And now taking supremum over small t, we will obtain that that the norm of X, the supremum norm epsilon in C, that is the supremum on 0 capital T of X epsilon T minus Z epsilon T is less or equal than epsilon B, so the supremum of B T E, I mean here is some constant. But the most important thing is that here we have epsilon. And if epsilon goes to zero, we have that this one will go also to zero as epsilon. In particular, this implies that if we consider limit epsilon goes to zero, epsilon logarithm the probability that the norm X epsilon minus Z epsilon is larger than delta, then you see that if delta is fixed number that is positive, then this difference goes to zero for every omega, because this estimate we obtained pointwise for every omega, and that it will mean that when epsilon is sufficiently smaller, this event will have the probability zero. It will be the empty set, and therefore will have the probability zero, but as we argued, that logarithm of zero, it is minus infinity, therefore here the limit is minus infinity. And later you will see that this condition is enough to claim that if one family satisfies large deviation principle with some rate function, then another family satisfies the same large deviation principle with the same rate function. We will see later that this new equation in terms of large deviation is not different as this equation, for which we know what the large deviation principle is, and therefore we can immediately conclude what the large deviation principle is for that family of equations. Okay, now we need the definition to be able to start develop this idea. It is, we first assume that, as before, let E, comma D be a complete separable metric space. Metric space. And then we say that two families psi epsilon and maybe let's write that fully. We say that families psi epsilon and eta epsilon are exponentially tied I'm sorry, exponentially equivalent. Equivalent. We discussed exponential tightness before, and exponential tightness is important to make the connection between a weak and strong large deviation principle. But here they are exponentially equivalent. It means that if for every delta larger than zero, the limit that epsilon goes to zero of epsilon logarithm the probability that the distance between psi epsilon and eta epsilon is larger than delta is equal to minus infinity. By the way, you can ask the question why we need actually here assume that we work with nice metric space, in particular that space is separable. But if you have the separability, then this event, then actually this one is event. It is measurable. In general case, it is not true, and therefore you cannot consider the probability that this type of the probability. So here the separability, for instance, is now we can formulate the proposition. Proposition 11.3 that the families let families psi epsilon and eta epsilon of random elements in M in a separable metric space in a separable metric space. By the way, maybe for the definition, we don't need to assume that the space is complete. So let's remove that, for instance, it seems that for this proposition, we don't need to require the completeness. Okay, then is in a separable metric space, EM be exponentially equivalent, be exponentially if okay, then the family psi epsilon satisfies the large deviation principle with a good rate function I, if and only if and only if the same large deviation principle holds for eta epsilon. The same large deviation principle holds for eta epsilon. Okay, once again, we require that families are exponentially equivalent on a separable metric space, and you know that then one random variable satisfies the large deviation principle with good rate function. Here we use goodness. If and only if the same is true for the second family of random variables. And then when we come back to the example that we had here, you see that this assumption is satisfied. This is a distance in the space of continuous functions. And we have the large deviation principle for this for family of random variables z in the space of continuous functions with a good rate with some good rate function. Therefore, immediately we can conclude that that family also satisfies the large deviation principle. Now we want to prove the proposition. Then suppose that the large deviation principle holds for psi epsilon with rate function I. And now we want to show that the same large deviation principle holds for eta. For this, we need to show the upper bound and lower bound. We start with the upper bound. For that, we fix an arbitrary closed set. Actually, upper bound or eta epsilon. We fix F, that is subset of the space X closed, and denote uh, denote by F delta. It is the epsilon. It is the closed epsilon neighborhood of F. Actually, it is all points from X belonging to F, such that the distance between X and F is less or equal than delta. Well, the distance between the point X and F is denoted as the closest distance between X and some point or X and points of from F. It is infimum over all y over F d of X comma y. In other words, if this is your set F, then the epsilon neighborhood, it will be, it's maybe complicated to draw this set. It is that, so here the distance should be equal to delta. It is F delta. Then for this set, we can, and now we want to estimate, first of all, the probability that eta epsilon belongs to F via the probability that eta epsilon belongs to F and the distance between eta epsilon. Maybe I will move to another page. Between F, eta epsilon belongs to F, and then the distance between eta epsilon and psi epsilon is less or equal than delta, plus the probability that psi epsilon eta epsilon is larger than delta. We do that because now we can here, since eta epsilon and psi epsilon are not, so the distance between them is not larger than delta, then if eta epsilon belongs to F, this implies that psi epsilon must belong to closed delta neighborhood of F. For we can estimate this by the probability that psi epsilon belongs to F delta, and then plus the probability that the distance between psi epsilon and delta and eta epsilon is larger than delta. And this is for every epsilon. And now using that the exponential equivalence, we can, and the fact that this set is a closed set, you can consider that as an exercise to prove that closed epsilon neighborhood is a closed set. We can, we see that limit epsilon goes to 0, epsilon logarithm the probability eta epsilon belongs to F is, first of all, we estimate that by the limit supremum of epsilon logarithm, and here we have the sum of two probabilities. And then you remember that the logarithm of sum of two sequences, we can write, we can split that on two logarithms. For we did that, I would say many times, that will be maximum between maximum between the limit that epsilon goes to 0, epsilon logarithm the probability that psi epsilon belongs to F delta, and then limit supremum epsilon goes to 0 epsilon logarithm the probability, the distance between psi epsilon and delta is larger, and eta is larger than delta. More bracket. And now, as I already said, we want to use here that this set is closed and psi epsilon satisfies the large deviation principle. And also we want to use the exponential equivalence here. Therefore, we will get that it is less or equal than maximum between minus infimum of I of x, and then we have x belonging to delta, to f delta, comma minus infinity, and this is of course minus infimum. X belongs to f delta I of x. Okay, you see that we obtained, we estimated that limit by that infimum for every positive delta, or for each positive delta. And now we want to send delta to 0. And here we can use the fact that delta is a good rate function, since, I is a good rate function, since I is a good rate function. One can show that the infimum x belongs to f delta I of x is it goes to the infimum of I x belongs to f as delta goes to 0. And that is exercise for you. And I will formulate that as an homework exercise, and you will see it on my webpage. So therefore, this implies the upper bound, right? Because when you pass to the limit, this object goes to minus infimum I of x. X belongs to f itself. And it is exactly what we need in the upper bound. Now, to show the lower bound, we need to proceed that slightly differently. Then it is lower bound for atom epsilon. And here we fix an open set, that GB open set, and X belongs to G. So you know that every point of open sets belongs to that set with some neighborhood. We have the following picture. It is a set G, and then you take some point X, and this X will be here, will be completely in G with some neighborhood. Therefore, the distance between X and complement of G must be strictly positive. So if you measure the distance between, this distance, it is strictly positive. So therefore, we note that then delta distance between x and the complement is strictly positive. And then we take delta so small, such that delta is 3 delta is smaller than the distance. Oops, I'm sorry, not epsilon, it is complement of G. And in particular, for this choice of delta, we will have that the ball, then we have that the ball be delta is contained in G. Sorry, it is completely in. So the ball is the center at point X. It is in G. Okay, and now we estimate. The following probability: the probability that psi epsilon first belongs to the ball. And also, as before, it is less or equal than the probability that psi epsilon belongs to the ball of radius delta at the center at point X, and then distance between psi epsilon and delta epsilon, oh, I'm sorry, and eta epsilon is less or equal than delta, and plus the probability that the distance between psi epsilon and eta epsilon is larger than delta. But now look, if you have that the ball, okay, first of all, the ball is a subset. This delta is chosen by such a way that the distance between x and the complement of g is, so that you have this inequality that actually 3 delta is smaller than the distance between x to the boundary. Then when you consider a point, any point psi epsilon from this ball, and you also consider eta that has that distance between psi and eta is less or equal than delta, then of course, so this eta must be in the ball at least of radius 2 delta. But the ball of radius 2 delta also belongs to this set G. Therefore, you can conclude or you can estimate that eta epsilon must belong to the set G. So it is a probability that eta epsilon belongs to G. And then plus the probability that the distance between psi epsilon and eta epsilon is larger than delta. And now we want to estimate, to get the estimate in lower bound. First of all, let's say that using the large deviation principle for psi, we get psi epsilon, we get the following, that first of all, the rate function is less or equal than minus infimum over the ball. This y belongs to ball of radius delta of x, I of y, right? Because the point x belongs, because x also belongs to the ball, and this I of x is larger or equal than infimum over the ball, but here you have minus, therefore you have the inequality in this direction. But now this ball is an open set, and psi epsilon satisfies the large deviation principle. In particular, it satisfies the lower bound for the open set that is ball. Thus you have that is less or equal than lim info epsilon goes to 0 of epsilon logarithm the probability that psi epsilon belongs to the ball of radius delta with the center at x. And now we estimated that probability by the sum of two probabilities. Then we can continue. It is less or equal than lim epsilon lim inf epsilon goes to 0 epsilon logarithm, and here the sum that eta epsilon belongs to G plus the probability that psi epsilon, that the distance between psi epsilon and eta epsilon is larger than delta. And now, similarly, as we showed for the upper limit, you also can show for the lower limit that this can be estimated by maximum. But now between lim inf epsilon goes to 0 of epsilon logarithm the probability at epsilon belongs to g, comma, and then lim sup epsilon goes to 0, epsilon logarithm the probability that the distance between psi epsilon at epsilon is larger than delta. And you see that it is that this limit it is equal to minus infinity by the exponential equivalence, and we come to the conclusion that it is equal to lim epsilon goes to 0 epsilon logarithm the probability at epsilon belongs to g. And this was done for every point x from the open set G. Of course, if you take the supremum of the left and right hand side of this inequality over x belonging to G, then you will get the following. Then also you will have the same inequality. Then you will have that supremum x belongs to G of minus in I of x, but this supremum it is equal to minus infimum x belongs to G, and that supremum is less or equal than lim. I'm sorry, I forgot here to write the lower limit. Epsilon goes to 0, epsilon logarithm the probability at epsilon belongs to G. And this finishes the proof of the proposition. Therefore, we get the state. Okay, and next time, I'm sorry, last time we also considered the case when we had some family of random variables, and then we change a density of that family and obtained a new family of random variables. And then we showed that in this case, also we have the large deviation principle with another rate function. And now also we want to prove for that for this kind of exponential equivalence, or also for this time of change. But now we will assume that that actually this factor in the density, because we had e to the to some power, and if it goes to 0, then also we have a chance to get the same large deviation principle. Let me first of all formulate that, and then I will so repeat what I said somehow, maybe somehow differently. So we consider now a family of random variables or random elements, random variables, psi app. But now I assume that it was like in the previous lecture, we have the discrete family on a metric space. In, and we assume that we have measurable bounded functions. Bounded functions Kn from E to R. And then we define new family of random variables, a new family at the epsilon, I'm sorry, at the n, with the following given distribution, with the probability that eta n belongs to A is equal to 1 over Zn, it is the normalizing constant, and then e to the power e to the kn of psi n divided by an, the indicator of psi n belonging to A. For every A, that is Borel measurable set. On E, when this Zn, it is the expectation of that exponent. Because with this Zn, you will get exactly the probability measure. An. And I would like to recall you that, that last time we also considered the function k that was a bounded and continuous function. And then we obtained it, and it was independent on n. We had only one fixed function. And then we obtained that considering this family of random variables with k independent of n, we came to another large deviation principle with some given rate function that depends on k. But today we are going to assume that this Kn will goes to 0. And then we will show that in that case, the large deviation principle will be the same. Also, it is sometimes also it is the useful statement that has an applications, and so that statement is formulated as follows: lemon 11.7. Let a family of random elements satisfies the large deviation principle. Okay, let a family psi n satisfies then large deviation principle in a metric space E with rate function I. Let also eta n be as above. And or for measurable bounded functions Kn with satisfying that Kn uniformly goes to 0, goes to infinity. The supremum x belongs to E, and then you have Kx, and it is 0. Then the family eta n satisfies the same large deviation principle. It means that satisfies the large deviation principle in space E with rate function I. And now here we will not use the exponential equivalence, because you see for the exponential equivalence you need to have random variables defined on the same probability space, and then you have to and then you need, and for that random variables you need to be able to say something about the probability of that for the distance between that random variables. Here we had one family of random variables, xi epsilon, xi n, and then we built another random variables eta n that could be defined on a different probability space, but their probabilities is defined like that. So therefore, I mean, it is not straightforward to build a good coupling for that, but it is much easier here to directly prove the lower and upper bound and show that both of them are the same as for random variables xi. And it will be the main idea of the proof. We will just use the definition. Proof. We also start from the upper bound, let f from e be closed, and then we consider the limit that n goes to infinity, an logarithm the probability that eta n belongs to f. Now this probability we can this probability we can write as follows according to the definition of eta n. It is the upper limit of an logarithm, and then we have 1 over zn, the expectation of e to the power kn psi n divided by an, and then indicator function psi n belonging to f, and it is equal to we use the fact first of all that here we have a product, and therefore this logarithm we can write as the sum of logarithms, and it is lim sub an with minus logarithm of and Zn, it is the expectation of e to the power kn psi n divided by an plus an, and then logarithm of this term that we will copy. Okay, and now the idea is the following. We just want to estimate we want to estimate that probabilities. In particular, we want to estimate this term with supremum. Therefore, when we will put here supremum, we need to move this minus outside the supremum. Here you will get infimum. Then we will move infimum here. You will have infimum here. And then you can write here like two minus, and one minus you can move outside. Therefore, you will have minus supremum of minus kn. But this supremum of minus kn you can estimate by minus supremum of the absolute value of kn. Therefore, we will get it is limit n goes to infinity, and here you have minus an logarithm expectation of e to the power minus supremum kn, absolute value of kn divided by an, and plus. And then also here we will put supremum, but here since here is a sign plus, then we will have supremum here, then we will move supremum here, we can move supremum here, and then you can move supremum there. Therefore, it is plus an logarithm of the expectation of e to the power supremum, it is supremum here, kn, absolute value, divided by an, and then you have the indicator. But what you can do next, you can forget about that expectation, because this is a constant, an expectation of constant, it is the constant. And that also is constant, you can move it outside here. Can move that outside of the expectation. So therefore, you will get for the first term. You see that you will have the logarithm x and exponent that will kill each other, and then you will get minus an multiplied by minus supremum kn divided by an. Minus and minus will disappear, and an will disappear. Everything what you will obtain, it is this supremum. Then we can continue the estimate but maybe I will copy this the left hand side and put it here, and then I will continue. It is less or equal of lim n or n goes to infinity. It is lim sup. And then, as we said, we just have supremum of the absolute value. Supremum of the absolute value of Kn. Then plus. Then here you see also you see the exponent that you put here, and you have the logarithm of product. Therefore, you can split that on the sum of two logarithms. And for the first logarithm, you have a similar situation as you had here. So therefore, also it will be plus supremum Kn. And then it remains only that that an logarithm of expectation of indicator. But expectation of indicator, it is a probability. We will write that it is plus an logarithm of the probability that psi n belongs to f. But now you see that these terms, they goes to 0, and therefore that is equal to limit goes to infinity an logarithm of the probability of psi n belongs to f. But this probability, but psi n satisfies the large deviation principle. It is minus infimum over the set f of the function I. And that it gives us the upper bound. We started from here, we obtained that. And now similarly, also we can get the lower bound. And start from that from the next page. It is maybe I will copy some part and then we will make some changes. Now we have the lower limit. It is here of that probability, of this probability. Then, as before, just using the fact that this probability is given by that formula, we just write it here, but also we need to change that line to that lim inf. And then also you can continue like writing that as a product. And then now you estimate similarly, but now you want to put, but now you want to put here infimum. But if you put infimum here, then you move this infimum outside, or you move minus, so you move infimum inside, or you move minus outside, you will get supremum here. But this supremum logarithm is monotone increasing function. You can put a supremum here, then you can put supremum inside the expectation. You can put supremum here. And then the supremum of k you can estimate by supremum of the absolute value. Therefore, we get that we started, you remember, we started with infimum, and then we come to the supremum here, because here was 1 minus. Therefore, you have the estimate from the another side. It is lim n goes to infinity minus an logarithm the expectation of e to the supremum kn divided by an. And then plus, and then plus, and then you do the same trick here. You have infimum, you put infimum here, just you want to estimate that term by the infimum over the complete, I mean, then you have, you will have like infimum there, and you have infimum here, and then you can come to the infimum inside. And consequently, with this infimum, you can also, again, you want to have supremum, but this Kn, you can write that like infimum minus minus Kn. And you take one infimum and move outside. So therefore, you will have minus supremum of minus K. But this you can, but this will be but then this you can estimate like minus supremum of the absolute value. So therefore we have here it is larger or equal than plus an, the logarithm of the expectation of e to the power minus supremum kn divided by an. Okay, and then you have the probability. Or I'm sorry, you have the indicator, right? Psi n belonging to the set G. I'm sorry, I forgot here everywhere to change also the set G, because now we started with the estimation for the open set. I didn't write that. We need to say that here that G is open. And therefore, as before, you will get that this is lim inf, and then you have minus 2an, no, I'm sorry, minus 2 supremum kn, and then you have plus an logarithm, the probability that psi n belongs to G. That is larger or equal than minus infinity I over G. Because, again, because this goes to 0 by the assumption, and the set G is open, and psi n satisfies the large deviation principle with the open, so therefore in particular it satisfies the lower bound that has exactly this form. That finishes the proof of our statement. So therefore today we discussed with you that in some cases when one family is sufficiently close to another family, or if you make the change of density by such a way that this density that this density doesn't grow somehow like exponentially fast, then in this case you see that you will have the same large deviation principle. The large deviation principle is not changing. Okay, actually it is everything what I wanted to discuss with you today, because tomorrow, next Friday, we are going to talk about the application of large deviation theory in statistical mechanics. In particular, we will consider some model, and then we will try to apply our knowledge of the large deviation principle or the technique that we developed to say something interesting about the properties of that model in statistical mechanics. So therefore, I don't want to start the topic today. We will finish today a little bit earlier. So I thank you so much for your attention.